everyone and welcome to CSCult. In today's video, we are going to discuss about the hard problem from bit manipulation of module 1. Count total set bits. The problem statement given here is that we have a number n and we need to find the total count of set bits for all numbers from 1 up till n. Alright, so first let's see what are set bits. As we all know, every number has some binary representation. For example, 1 can be represented as 1, 2 can be represented as 1, 0, 3 can be represented as 1, 1, 4 can be represented as 1, 0, 0, 5 can be represented as 1, 0, 1, and so on and so forth. Alright, so what are set bits? Well, set bits are the number of ones, that means the number of on bits. The number of on. And when I say on, I mean the bits that are equal to 1. For example, here we have set bits 1, here again we have set bits 1, here we have set bits 2, here again we have set bits 1, and here once again we have set bits 2. Right. So for example, let's say our input is equal to 4. So if n is equal to 4, we will check for all numbers from 1 up until n. So for 1, 2, 3 and 4. So as you can see, we have already defined the number of set bits for 1, 2, 3 and 4, which are 1, 1, 2 and 1. So if we calculate the sum of these 4 numbers, we'll get the answer, which will be equal to 5. If here n was equal to 5, then we would have calculated for 1, 2, 3, 4 and 5, and then our answer would have changed to 1 plus 1 plus 2 plus 1 plus 2, which would have been equal to 7. Alright, so how do we solve this question? Well, there are two methods. First, we have the naive method, that is simply loop over all numbers and find individually the number of set bits that they have using a function. And the second method is a little tricky. The second method is little tricky but logical. The complexity that these two methods offer us are O of n, and the other method offers us O of log n. Alright, so the first method is pretty easy. Alright, so the first method is pretty simple. We just have to loop over all the numbers and define a function that takes in a number and outputs the number of set bits. Alright, for example, let's say that we have this function called count set bits. Now, if I input 3, it should return 2. If I input 5, it should once again return 2, because 5 can be represented as 1, 0, 1. If I input, let's say, 7, it should output 3, because 7 is represented as 1, 1, 1. Alright, so that is the first method, the naive method. Alright, what is the second method? Well, for the second method, let us take a slightly bigger example. Alright, let's say we have n is equal to 11. Now, first off, you might notice that we just have to solve from 1 up until n, but I have included 0 here, but it doesn't really matter because 0 is anyways, it does not have any set bits, and I have only included it for the sake of understanding. Alright, well, let's say I have a number n is equal to 11. I have gone ahead and already written out the binary representations of all numbers up until n, and let's see if you can spot a pattern. Well, I do. You can see here that up until 7 there is a symmetry here. If I check these numbers column by column, yeah, so I can see that there are an equal number of zeros and an equal number of ones. Same goes here and same goes here. So basically what I can do is that I have the same number of ones in each column, which in this case is 4, and there are 3 columns. So I have 12 on bits, set bits. Alright, so this solves this part for me. But in, let's say we don't, here we know that n is equal to 1 and we just saw these here. But let's say we don't know what these are. How will we calculate these? Alright, so the first step would be to find the nearest perfect square which is less than or equal to n. In this case, we have the nearest perfect square to be 8. Alright, so the numbers before the nearest perfect square form a perfect symmetry, through which we can calculate the number of set bits in those numbers. Now how? So we know 2 to the power 3 is equal to 8. The formula that we need here is 2 to the power of 3 minus 1 multiplied by 3. This will give us 12. Let's take this for some x value. For example, we have some perfect square which is 2 to the power x. In this case, the number of set bits in all numbers before that number, before the perfect square which is equal to 2 to the power x, will be 2 to the power of x minus 1 and multiplied by x. So this solves this part of the problem. Now for the remaining part. Here you can see that this column will always be equal to 1. This column. Because here we have these many zeros, so this will by default be always 1. Because if the number was so big that there was a 0 after this, then that would be another number less than equal to the perfect square. So that is a completely separate case. In that case, the perfect square would be a number below this, but as this is we just have till 11, then this column will always be equal to 1. So the number of set bits in this column will be equal to n minus the perfect square plus 1. Alright, so this solves the problem till here. Okay, now what about the remaining numbers? Well, if I find out the remaining numbers, the remaining digits, the remaining binary representation, and I convert it to decimal, I get 0, 1, 2, and 3. And if I pass this number 3 through this count function once again, then I can find the number of set bits here. So this is basically a recursive function. So the formula for this will be count of n minus perfect square. Alright, so what is the final formula? Well, the final formula is equal to 2 to the power of x minus 1 multiplied by x plus n minus perfect square, which I'm representing by ps here, plus 1 plus count of n minus perfect square. And because this is a recursive function and the number of n is constantly dividing by more than just half, therefore this gives us a time complexity of log n. Alright, so now let's start coding the solutions. First, we will code the naive solution. Alright, so let's first include the libraries we need, IOStream, using namespace std, and I will use two functions. One will be count set bits, will take an int x and it will output the number of set bits in x, and the other will be a main function. This will take in the input. Let's first define this. We have int n, which will be the input. Let's take the input here. Now we'll need another int ans, which will be equal to, let's initialize it with 0. Now we need to loop over all the numbers starting from I is equal to 1, I is less than or equal to n. That is, we need to include n, that's why I have put an equal sign over here. And let's increment it by 1. We will use ans plus equal to count set bits, which will give us the number of set bits that the number I has. We'll pass I here. And the output will be the answer. Alright, now let's come to the main part, the count set bits part. So here we will have an int count initialized to 0, and we will run up until x is more than 0. Now if x mod 2 equal 1, that means that there is a binary bit. We are basically counting all the bits starting from the right side. Alright, so we will increase count and we will divide x by 2 and return count. Alright, let's try running this. Let's give the input as 4 and we get the output as 5. Let's try the other test case that we have here. Let's input n is equal to 17 and let's see what do we get. And we get the number 35. That means that this answer is correct. Alright. Now let's comment this part out. And now let's write the other method, the trickier but more efficient method. Alright, first we'll include the libraries we need. IOStream using namespace std. Alright, I guess we can copy this part as it is pretty much the same except for the loop. Now answer will be equal to count set bits, or actually let's rename the function to just count, and we'll pass the number n, and this should give us the answer. Let's define count now, int count, and we get the number x. Alright, so how do we begin? First off, if x equal to 0, then we return 0. If x equal 1, then we return 1. Well, these are the corner cases. in case these occur, the rest of the code might just call itself again and again, and it might over exceed the heap and run into an error, an infinity loop sort of recursion. So it is necessary to define the corner cases. Alright, now let's take an int sq, which means the square, and let's initialize it to 1, and then another int I, and this we'll initialize to -1. I'll tell you why I've initialized these to these specific numbers, but for now just go with it. Alright, while sq is less than n, we'll multiply sq by 2. We get sq is equal to sq multiplied by 2 and I plus plus x. We have x here. Okay, so when we run over this loop, what will happen is that we'll get sq of we'll multiply sq by 2, and the moment after it exceeds n, this condition will become false. So basically we'll get the closest perfect square of 2, which will be just more than n. So to prevent that, we'll have to divide sq over here, to sq by 2, and I here is counting the power of sq, so it is incrementing by 1 every time we multiply it by 2. Now I can initialize it to 0 also, and then later subtract I by 1, but I chose to initialize it with -1, and every time it adds, so I don't have to decrease it by 1 later on. Alright, now this is our formula. So now we have the perfect square, and we have the power to which we need it. So our answer, we have x and we have 2 to the power x. So and our answer will be 2 to the power of x minus 1. So that will be basically 2 to the power of x divided by 2 multiplied by x. Alright. So here we'll have int ns equal to sq divided by 2 and multiplied by I. Then we will add n minus the perfect square plus 1. So that will be x minus the perfect square, which is sq plus 1. And finally, we will add count of n minus the perfect square. And we will return the answer. Alright, this should be it. Let's try running it. Sorry, this should be x here. Alright, compiled. Now, let's see. Let's try the input with 4 first. Alright, there is slight mistake. Oh, right. Right. So when we were testing it, well, the condition was that we need to check the closest number. Well, I forgot to do this. Sq is less than or equal to x, because if x itself is a perfect square, then it shall just simply take all the numbers before it and just add 1. Alright, let's try this again. And that's it, we get 5. Let's try with another test case. With 5 we get 7, and with another test case with 17 we get 35. So right, we have successfully solved the hard problem of bit manipulation from module 1. I hope you understand, and thank you.